Converting the base of a number from binary to hexadecimal is much easier if you can remember or easily list the binary nibble representation of each hexadecimal figure. In the denary column you can see I'm just listing all of the numbers starting at 0 and going all the way up to the number 15. You can also see in the hexadecimal column I'm counting up from 0 all the way through, all the way up to 9. Hexadecimal has figures for 10, 11, all the way up to 15, and these figures are A, B, C, D, E and F as shown here. We write down A to represent the 10, B to represent the 11, C to represent the 12, 13 is represented by D, E represents 14 and F represents 15. In the binary column we represent 0 by 4 bits, and these 4 bits we refer to as a nibble. Now the least significant column of the nibble goes 0, 1, 0, 1, 0, 1 all the way down to the last position. The next column goes 0, 0, 1, 1, 2 zeros, 2 ones, 2 zeros, 2 ones all the way down to the bottom. The next column goes 4 zeros, then 4 ones, then 4 zeros, then 4 ones all the way to the bottom. The remaining column, well, here we write 8 zeros followed by 8 ones all the way to the bottom. Now this is demonstrated a way in which we can quickly list all of the binary nibbles starting at 0 going all the way through to 15. Now it's actually easier if you try and remember these, but if you can't and you need to convert from binary to hexadecimal, I recommend you get used to simply writing this table down quickly. Let's look at an example. What is the binary representation of the hexadecimal number E? In other words, 14. Well, we can see we've got E, so we look for it in the table and we look for the binary equivalent which is right next to it. Therefore we can say E is the same as the following binary representation. What is the hexadecimal representation of the following a binary number? Well, there's the number. We look for its position in the table and we can see it's A. Therefore the binary number is the same as A, which we know is 10. What is the hexadecimal representation of the following 16-bit binary number? Well, you always start at the least significant bit, which is this one here. Then you count 4, 1, 2, 3, 4, and then you put a dividing line at that particular point. You then count off the next 4 bits, as you can see here, and then you put another dividing line at this point. You then count off the next 4, as you can see here, and put another dividing line. And in this example we can see there are 4 bits left. Here we can see we're highlighting the nibble that we have to look for in the table, and we can see it's in this position which corresponds to the position of E. So we write E down, as you can see. We then move to the next nibble and we can see that that's the position in the table and that corresponds to the figure 1, so we write the figure 1 down. We then do this for the next nibble. As you can see here, we locate it in the table and we can see in fact that this is A, so we write the A down. We now move along to the next nibble here and we locate that in the table and we can see that that corresponds to 8, so we write the 8 down. Therefore, this binary number can be represented in hexadecimal by 8A1E. Let's consider another example. Start at the least significant bit and break up the long binary number into nibbles, as you can see here. It is then a case of going to each nibble in turn and locating it in the table, and here you can see we wrote D down. Let's have a look at the next one. That's the number in the table, which we can see is 9. If we go to the next nibble, we can see it's the first entry, which is 0. And then we've got here 4 ones, which is the last entry, which gives us F. So we've wrote all of those down. Therefore, the original binary number that I'm writing down here can be represented in hexadecimal by F09D. Remember, always start the grouping of the binary nibbles at the least significant bit. So for example, if we look at this, that's the least significant bit there. This is the most significant bit. So you must start your groupings from here.